Um, Hello? Hello? Okay, it works. Welcome to the Mighty Energy Seminar Series. This is the second year of this seminar series, the first talk. First, I would like to introduce our committee members. This is a campus-wide Mighty Energy Seminar Series, so it consists of members from various departments. And my co-chair is Amy, Professor Glassmeyer from this is urban planning, if I'm correct. And we also have Professor Millie Dresserhaus. I'm not asking everybody to stand up. Professor Robert Wanderhurst and Fiona Marie, Christina Preether, and Ed Stanford, Amy Smith. So we have this seminar series is once every month, the first Tuesday of the month. So we have a list of very distinguished speakers. There's still one or two we're still working on, but you won't be disappointed. So with that, I want to now turn to introduce our first speaker. This is Professor Jacob Carney, and he will be talking about the next phase in large-scale solar thermal power generation. Jacob was an assistant professor at the Mechanical Engineering Department of Stony Brook, from 84 to 89. And he moved to Weizmann Institute since 1989. And he, in addition being professor at the Weizmann Institute, he also has been doing a lot of real-world applications, including CTO of heliofocus LTP. His research centers on the utilization of concentrated solar energy. He's interested in the development of new methods for concentration, absorption, conversion, transmission, and the storage of concentrated solar energy, and implementing this method in genuine solar power conversion systems. I just want to say a few words. I first met Jacob in 2006 in Department of Energy Solar Energy Workshop. So there was a document on the solar energy utilization. And Jacob and I co-chaired the solar thermal topic. And I knew at the time I didn't know anything about solar thermal. I worked on materials. Jacob was the person that really organized the solar thermal in terms of the research. So today I'll have the opportunity to learn more together with you about his research in the solar thermal area. And let's welcome Jacob. Thank you.
Thank you. Thank you again. Okay, when you give a talk like this, with a general topic like that, usually you worry if half of the audience would be bored to death and the other half will be lost. So the best way to alleviate the problem is to move fast. So this is what I'm going to try to do, and also there's a lot of material to cover. And we'll move fast and stop me in the middle if you want to, or ask questions in the end. I'll try to make it as organized and as simple as possible. Okay, first of all, what do we need to do? So I think I'll take this, we have any kind of instrumentation too. Well, you can look at the figure, and what you see here is the U.S. electricity generation in 2008. And you could see that renewable account for about 10%, a little less, coal about half, natural gas about 20-some%. But out of the renewable energy, out of the 9.5% of renewable energy, most of it is hydropower, and solar account to 0.6% of the 10%. Okay? Literally nothing. Now, we know that solar is the most abundant energy resource of the United States as well as in the world. We have more solar energy in the Southwest desert than we need to supply this country for many years. So why? Well, the reason is simple. It's expensive. Solar energy is expensive. So what do? You have to figure out ways to make it cheaper. And that's the idea of developing solar energy. Okay, so what options do we have? Well, certainly there are two categories that we all know about. One is concentrated solar thermal, and the other one is photovoltaic. This talk is going to be on concentrated solar thermal, so I'm going to let you head start. I'm going to say that it's better, so the PV people, please forgive me just because I'm talking about solar thermal, and the next lecture we'll talk about PV. That will be better. So within solar thermal, okay, good. Within solar thermal, we have basically 3 or 3.5 options. Parabolic trough and linear Fresnel is almost the same technology. Central solar receiver and dish engines, and we will talk a little bit about each one of them as we move along. And let's just see what the options are. There's just basically solar thermal is a system where electricity is then generated by a heat engine that is driven by solar energy. Yes, you take the combustor out and you put the heat using solar energy. So the main components of a solar thermal system always will be the radiation collection area and collection and concentrating, and the power conversion unit. The power conversion unit, unlike normal power conversion unit, does not have or may have a combustor, but generally has a solar receiver that converts radiation to heat, and the heat engine of your choice. So the first system that was developed for solar thermal system was a trough-based system or linear concentrator. The idea here is that the light comes onto a trough-shaped collector that concentrates the light onto a tube. The light comes in, concentrates this tube, so the light is folded in one direction. Because of the similarity to trough, it was dubbed trough system. This is the most mature sort of technology there is, actually, certainly most of solar thermal. The only mature solar thermal technology there is. There are 380 megawatt installed in California, and much more is being built now. This is what a solar trough plant looks like in near Barstow or Kramer Junction in California. And right here, this picture shows a variation of this where instead of using glass collectors that track the sun, there are Fresnel reflectors, and the tube here is stationary. So this is sort of a simplified approach with somewhat less optical efficiency and hopefully cheaper. Second option is the solar tower. You have a stationary target. It's also called central receiver. You have a central tower, fixed tower in the middle, and Fresnel reflector, or as they're known as heliostat, that track the sun and reflect the light into the tower. Here is a demonstration plant that was built again near Barstow in California, 10 megawatts. They built it first for steam generation and then using direct steam generation. Then they use molten salt to generate the steam and use some storage. And this is the largest solar tower that was used until recently, where a facility like that was built in Spain. We'll talk about that too. Dish engines. Dish is a wonderful optical technology developed by the Chinese during the Qin dynasty 3,500 years ago, roughly. They use it as a solar cooker. Da Vinci then did some kind of manipulation and actually had an heat engine. He was way ahead of his time, so he made a spherical dish with a tubular engine. I'm telling you, and a lot of people invented it after him. And so the nice thing about a dish is it tracks the sun all the time, and it always points in the sun, so the optical efficiency is the highest. And the problem with the dish is it's a lot smaller than the other systems. So, and here is a picture of experimental or prototype dish with Stirling engine on them in Albuquerque in Sandia Lab. Okay, that's Solar Thermal 101 is over, and now we go to our problems. Well, the fundamental requirement of electricity power supply is give it to me now, and give it to me when I want to and when I want to. No arguing about it. When we go and we want electricity, we don't care where it comes from. The light now is blinding me, and it's got to be on, and it's going to be on whether we like it or not. I used to say in Israel, all the kids come home from school at 2:30 in the afternoon, and what do? They all go, all the kids, all the country come home at 2:30 in the afternoon, and they all go and open the refrigerator door and stare at it for 10 minutes to decide what to do, right? Imagine that, what they do to the grid, the power utility. For 2:30, there is a tremendous peak. What happens? You got to supply power. And if there isn't enough solar or something else, the grid doesn't care. The customer doesn't care. So here are some problems that we may have with that. I like to use the wind example because it's very clear, and then go to solar. Intermittent energy supply just doesn't do that. I got this slide from a utility company in Germany, and they were the first one who made me aware of how much utilities hate wind. Okay? And why? Here are these guys, they've got this grid that they supply with roughly 17 gigawatt. That's a lot. Now, they know their load very well because they have a lot of experience. This is just November in Germany, so it's a little cold. This is a morning load, a little bit of a break in the afternoon, an evening load. Night is going down, and so on. Now, the variation from day to day are based on the fact there might be a weekend, or this is a colder day than that. But they know exactly what it is, and they can anticipate it and supply the power. Here comes the government, and it says, we are going to do wind power. And you have to buy, it's legislated, you have to buy wind power if somebody's going to supply it to you. And you have to buy whatever the supply. So they bought 3 gigawatt of wind power. And here is what the wind does. It supplies power when it can. What is the utility going to do on another day when there isn't wind, here or here? Well, they have to build another plant, another coal plant, or nuclear, or gas. They call it shadow plant because it doesn't exist. But it's there, they pay for it. It may work only 50% of the time that it could have worked, or less. It's a real loser for them. They could have used that and they didn't have the wind. So this cannot be a solution for a large scale. In a large scale system, you have to be able to supply according to demand. Let's go to solar. Let's go to Arizona. Here, this is again a wind example. This is the load in this city. It happened to be a tourist attraction, so the load in the summer is late in the evening. And this is what the wind does, ironically. Usually wind does come at night, but this is the situation there. So wind is high when you don't need it and low when you need it. This is an average. I'm obviously showing extreme example. It's not always like that. This is what solar would have done had it been there. Okay, still doesn't solve the problem. You have to have an ability to either hybridize meaning supply fuel when there isn't enough sun, or store solar energy. Okay, this is an example of how you can sort of shift part of the power to a different time, and obviously you could adjust according to load. With hybridization, you actually supply power whenever they need it. If there isn't enough solar, you turn on the combustor. Okay, it doesn't sound as green, but it's life. It's eventually going to get you more solar power, not less solar power into the system. Okay, so we have to select the solar technology. Unfortunately, photovoltaic does not give us an option for storage and hybridization. Storage and hybridization of solar energy is the same as with wind. You have to build another plant on the side. On the other hand, solar thermal enables you to store and hybridize solar energy. So because of that reason, and if no other reason is there, photovoltaics, I believe, will be a solution that mostly will be for highly distributed systems, and that's a lot of power. There are many, not in the United States, but many countries. Take, for example, India. 60% of the people that are not connected to the grid, so there's going to be a lot of distributed power, non-connected to the grid, that photovoltaics would probably be the choice there. Whereas solar thermal would be the answer for large-scale solar power, grid connected and so on. The key here is now that we're going to solar thermal, is we have to develop technology to both produce solar energy cheaply and to store solar energy and transport it. So let's see the difficult issue with solar thermal. Here is a fundamental problem of solar thermal. Well, the most efficient and lowest cost heat engine are large. Remember, I told you the solar thermal is basically a heat engine and a collection system. So one is driven by optical efficiency, the collection system, and the other one by engine efficiency. The most efficient and lowest cost heat engines are large. The larger it is, the lower is the specific cost. And many other advantages of being large for the heat engine. Well, when I'm saying large, you take a combined cycle plant, it typically will have a gas turbine for 200 megawatt or so, and steam turbine for about the same. So maybe 2 gas turbines and 1 steam turbine giving you 600 megawatt per plant or more. Just as a rough number. Well, the optimum engine size for parabolic trough is roughly 50 to 100 megawatt. And if we had time, I would explain why. The optimum size for central receiver, solar tower, is about less than 15 megawatt. And the optimum size for parabolic dish is something less than, or roughly about 100 kilowatt, 0.1 megawatt. All of them are a lot smaller than what you would optimum hope for. And to make matter worse, the optical efficiency of the lowest system, of the smallest system, is the highest. So here we have, on one side, we want to make the engine larger. On the other side, the optical system say go smaller. It's a real problem. What do? We got two ends to that very long stick. Well, the visionary says the next generation has got to address this problem, and we're trying to, and we will see in a minute how. How are we going to address this problem and reach cost parity with the conventional power plant? That's a challenge. Well, that was the visionary saying, but will we ever get to the next generation? Let's see. Now we go into the real world problem. Until now it was the thermodynamics problem we're not interested in. Let's look at the real world problem. Well, first facts. Right now, there are unbelievable opportunities for solar power plants to be built. You can go to Spain, or could 2 years ago, and now it's a little more difficult, but still can, and build a solar power plant that will have 5 times the cost of what it would be had you built a gas or a cost for electricity or gas or coal. And you still be making a lot of money because of subsidies. Okay? People are getting rich. The same thing happens with wind, too. And trough is the only mature technology that you could do it with. There's no other technology that is right there ready for you to build power plant. Well, so what are the developers faced with? They have several options. Option number 1, grab the opportunity, go build trough system as many as you can, as fast as you can, and make power and make money. Okay? This is low risk, short-term payback. Very, very tempting. Well, the other option said, okay, this is not going to go away. We're still going to have this opportunity for a few years or more. Let's develop a new technology that will be cheaper than trough, but it's only going to be commercially available in a year or 2. I'm just going to, if trough is going to produce electricity for 14 cents per kilowatt hour, I'll make something for 13 or 12, and I'll be in the market in 2 years, and I'll beat them. Now, really, I'm not solving the problem here. I'm not reaching cost parity with coal or natural gas. But I'm going to make a lot of money in 2 years, and I'm going to get trough out of the business. And option number 3 is develop a breakthrough technology that can reach cost parity, but it will take 4 to 5 years. High risk, longer payback. These are the options. Now, what would you do? What would you, come on, you're going to develop a solar plant. What would you do? Which option do you take? Hey, think about it. But this is a real question. People do it, have to decide how they approach it.
I go and build the simpler systems, because I know that today I'll get a lot of subsidies, so that's great. But in 2 years' time, I don't know what's going to happen to the economy. I don't know anything about it. So I may not get the opportunity to build anything.
Okay, so what you're saying, I'll build something I can do right now, and then in 2 years you'll build something else, or start building something else. Not a bad idea. I mean, well, here's our approach. I mean, it's not a general truth. It's just something that somebody who works in a university can say, I can do it. We want to do the long-term, lowest cost solar power. That's a challenge that we think is worthwhile for humanity, okay? We're not in the money-making business. We are thermodynamicists. What do we understand about economy? Okay? So we could do that. And develop a storage solution, because without this, you're not going to be able to do it at night or the evening, and certainly not going to be able to drive cars with solar energy unless you have a storage and transportation solution. And what the gentleman there said, a fast-to-market approach is acceptable if it leads to eventually long-term solution. If you could do a fast-to-market approach and then say, okay, I'll leverage that to eventually build a better solution because I'll have money to do it, because I'll learn some things that take more, makes a lot of sense. Okay? This is just what I'm suggesting. Everything else until now, what I said in this talk, was absolute truth, right? This is just an opinion. Okay? Okay, now we have to select a solar thermal approach. And how do we do this? So let's just assume for a moment that eventually people are going to build a large solar plants, and they're going to be able to minimize their cost in any way possible. Let's do about PV, about solar thermal. We can see what happens, how the PV industry is being able to lower costs. We'll see how trough is getting cheaper. So let's say everybody's equally smart and can build system at very low cost. Well, the bottom line will be that the cost driver of solar system is going to be the cost of glass and especially steel, because this is what the collection area is made of, or most of the system. And the way to minimize this cost is to become more efficient. If you're more efficient, then you need less collection area for a given megawatt that you produce. So you, as a general direction, go into increasing efficiency of the system to decrease cost. Let's see how we do it. Well, there is something that I dubbed the Fletcher principle. Let's try, and this is the only figure that will have some equation, I promise here. Fletcher was my mentor in solar energy in my early days at the University of Minnesota. Professor Ed Fletcher, he built a solar furnace on top of the mechanical engineering building, and they had parties there all the time during the cold, bright winter days in Minnesota. And he really was the father of solar thermochemistry. So one of the things that he said is, okay, what are the limiting parameters? The limiting we know that the limiting efficiency of a heat engine is Carnot. Okay, so right now we have, this is the Carnot efficiency versus temperature. And right here we have the Carnot efficiency. Okay? And then if you have a solar system and it use a receiver to heat this system, then your system will radiate. You have to put the solar through some kind of a hole, and the system gets hot, so it will radiate based on the temperature of the system, right? So this is the efficiency of the receiver. This is the input power, the solar energy, direct normal radiation, time the concentration, and this is the losses that you have. So together, the heat, so the ideal solar energy engine efficiency is this expression, which is a function of temperature, the efficiency is a function of temperature, and concentration. The higher the concentration, the smaller is the hole you have to put the power in, so the radiation decreases. So if we take, for example, a trough system, with all the selective coding and so on included, it's roughly 60, concentration of about 60. It's less, so with that, that's what it is. So look, the optimum temperature to use a trough system is about 400 degrees C. That is indeed where they're using it. Now, they're not using it 400 degrees C because that's the optimal temperature, because for some strange coincidence, the oil, which is transformed, the heat transfer fluid that they're using, can only work up to 400 degrees C. And there are many people now breaking their head how to make trough go to higher temperature, how to make better oils. Well, I think that would be a waste of money. Because if you go higher, and you can't change this efficiency, the concentration, you're not going to do better. What you gain by going higher temperature here, you will lose by the engine efficiency. Let's take a solar tower for a moment. A solar tower efficiency is related to its size, mostly. A very small tower can go to higher efficiency. But if we take, being consistent with what we said earlier, let's take a solar tower for about 10 megawatt, you can reach about a concentration of 500. And a concentration of 500 will give you a best working temperature of about 800 to 700 degrees C. That's very nice to drive a steam turbine at the highest. The steam turbine typically will want less than 600 degrees C. That's good, but it can't take you any higher than that. And The dish, which is very small, can reach a much better concentration, 2,000, so it could go to about 1,000 degrees or higher easily, and get to a higher temperature, and ideally to a higher efficiency. But remember, it's very small. That's a problem. So ideal life is not the same as reality. Dish has high efficiency. It has high theoretically high optical efficiency and high theoretical engine efficiency. But it's too small. So that's the bottom line of where the thermodynamic brings us. Here is real life. This is a facility just northwest of Seville in Spain, built by Abengoa. When you go there on a day that there is a lot of humidity, like after the rain, which we were fortunate when I was visiting there, you actually see the light. This picture was taken from the south side. You could see the rays coming in, almost like a picture of ray tracing. I'm telling you, this is a fantastic thing to see. It's so beautiful, and you could actually see here heliostat rays that didn't quite get there yet. They're on the way. They're coming in here. You couldn't make a better drawing of ray tracing than that. Gorgeous. But this, now you go to the north side. Look what you see. Where am I? This is real life. This right here is the aperture of your receiver. Look at where the light is. That's the way it is. The spillage is huge. Now, you can't tell right here exactly what how percentage goes in and what time, because obviously the camera is saturated. But you can tell that there is one heliostat that's pointing right here. And either they're here, they're not even getting in. These are heliostats coming from the east side. You guys are now sitting at the north. Okay? And this is how it is. The farther the heliostats are, the larger is their spot. And if you want to make large solar towers, you got to go farther away, and this is what you're going to get. Abengoa will be the first one to tell you their efficiency is very low, but they only want to maybe telling the truth because they've already built it. So what are you going to do? Well, we have a possible solution of how to deal with this problem. And it's sort of like trying to get the best of both worlds. First of all, you build an array of dishes, and in each dish you put a small turbine, a micro turbine. And these micro turbines typically work at 1,000 degrees. One day probably we'll be able to work at higher temperature, and they produce electricity. However, the air that's expanded and coming out of the turbine is still very hot. It's about over 600 degrees C, about 660 degrees C. So what we're planning to do is take that heat and deliver it to a large steam turbine collecting the heat from an entire field of dishes, and here have a steam turbine as a bottoming cycle. So we basically have, or we're trying to have, some kind of a compromise. On one hand, we are collecting at the best efficiency with a dish. Hopefully we'll be able to make large dishes that will, as large as possible, make it cheaper. And then the rest of the heat goes into a steam turbine. So we produce electricity from the dishes here and the steam turbine there, and that's combined cycle. Combined cycle is the most efficient way that knows to us how to make power. So this is, if this works, it will be a more efficient approach than, much more, and then what is used now. This is just to show how a single unit works. You have a a parabolic dish with a solar receiver and a turbine at the top here, generating power at upper temperature of 1,000 degrees, and then some of the heat at a lower temperature, about 600 or so degrees, goes to a central station. So just one solution, perhaps there are other just as good, to produce solar electricity as cheap as possible. I'd like to tell you what we did to enable this technology. Now, the issue was people had done concentrator before us, and they also have done engine before us. And the issue was how to make this device, this receiver that can take concentrated solar energy and convert it to heat at very high temperatures. So it was really a radiation to convection heat transfer problem. This is where we worked. This is the facility of the Weizmann Institute. It's a very nice solar tower. It's really a nice laboratory to do this kind of work because we have several working stations, and you could have many students' projects in different locations, and if something works right, then you can assign the floor to a single system. Right now, for example, our company Heliofocus is using the whole floor for its own work. And so they got a possibility to start with some idea and get to a scale of a real commercial system. We started with trying to put solar energy into a gas turbine. So this is just a chart of how the gas turbine works. You have air coming in, being compressed, then going into a recuperator. You may or may not have a recuperator in a turbine. From the recuperator, the air goes to a combustor and then to the expander or the turbine, and then back to the recuperator. And this air heats up the inlet here, and from here you put fuel system. And if you want to run it with solar, all you have to do is add a solar receiver right here with some concentrator. So this solar receiver have to work with the pressure that the compressor supplies, typically say between 3 and 30 atmospheres, and the flow rates, and it's getting air at temperature that may vary from 200 degrees to 600 and some degrees, and heats it up to 1,000 degrees or higher. And that fuel system is used only when there isn't enough solar energy. So the key was to develop this device here. And there isn't a lot of time to go in a lot of details on that. But here is, it's a long-term program. You don't get it done in one day. We built our first prototype in the early 90s. We work at very high temperature and pressure of about 20 bars and temperature 1200 to 1300 C. Worked very nicely. And that is this device here is our the foundation to all the ones that were built after that. We built then a system that was, I mistakenly thought that you go to a higher temperature is better, so we said, hey, let's build one that goes to 2,000 degrees. And we did, and then we found it has nothing to do with it because you can't connect it to anything. You don't want to work at 2,000 degrees of solar energy. It's a waste of time. You're only going to be able to work only very short time because remember, solar comes in the morning and it goes in the afternoon. Stay on 1,000, 1,200 degrees, that's fine. And then we built the first turbine, solarized receiver with a turbine. That was in roughly early 2000 here. And now we're working on our the fourth generation receiver. It's being built for the Heliofocus system. Here you see these guys. I have to show you this picture to believe me, it's really happening, right? So they're actually guys wearing those dark shirts, and they are putting this system up there on the solar tower. The station, here it is. And after that happened, I'd like to talk a little bit about how to make clean fuels. Okay? Remember, we need to solve the problems of how to make electricity cheap, but we also have to make fuels. Now, basically, the cycle goes like this. Okay? You get concentrated solar energy, you make heat, and with that heat, you promote a chemical reaction. That chemical reaction takes something that doesn't have any heating value, like water or carbon dioxide. You make a chemical reaction, you make a fuel, synthesize a solar fuel, you use it in the engine. What comes out is basically what you start here, and you can repeat this cycle. Okay? So this is how it goes. Now, I'm ready to stop right here. If you guys are exhausted, I can tell you how we do this. We can, it can be like for next time. Can be we can take a vote.
Actually, so tomorrow at the lunch hour from say 12 to 1 o'clock, there will be a more in-depth seminar given on the more technical side by Jacob. This will be in data center, and there will be pizza provided, and so you will come
pizza.
over, and if you will come in around 11:30. So, so I think it's the right timing.
Okay.
And I'm sure there are a lot of questions. I just want to warn you that I know Jacob likes the question and would like to wrestle his questions.
Yes.
Yes,
I was curious about the, first of all, thanks for a very nice talk. But I was curious about the efficiency overhead of the tracking power of those dishes. So how much of the total power you generate is devoted to tracking the sun in a typical
Negligible amount. I'll show you how these dishes track, and they're two kind of dishes or trackers. Okay, trackers can be used for heliostats or dishes. There is one that sits on the pedestal, and then you got two engines driving it up, and usually use it when the reflector is not more than, say, 150 meters square or 200 meters square. When you go larger, we use something called turntable. We make a track on the ground, and then you roll wheels around like that, and then the engine don't really have to take all the load of the drag of wind and so on. They just have to roll it around. You could, in the old days, you could put an axe like that to make to grind a cake, and it could do it all day long. So this engine can also. No, in terms of numbers, it's a fraction of a percent. Even not even that. Yeah. Also, remember, they don't have to work all the time. They work, they stop, and they correct themselves. Even they do, the motion is very small. Very small. The east and west motion is the most. Its engine works more than the elevation. The azimuth. What? It's very little. Yeah.
Questions?
Yeah.
Can you say just a few more words about the storage part of the equation?
Okay.
In terms of its maturity, how
Okay.
soon will you be ready to
Okay.
take care of a typical day, and balance it out a bit?
First, what is storage? What we're really trying to do in many different ways is to take carbon dioxide and make carbon monoxide and oxygen out of it, and water and make hydrogen and oxygen out of it. And if we're lucky, mix them together, the hydrogen and the CO, to make syngas. And now we have the ingredients to make any fuel you want. Basically, if you know how to make it at the right stoichiometric ratio for whatever you want to do. And this is what we're working on. Now, Jules Verne said in 1873, when he wrote a book, he says, at that time Europe was extremely polluted. Remember the movie Mary Poppins with the chimney guys going there and then dancing all over the place? But the place was really a mess because everybody would buy coal, put it in the house and burn it. It was a real problem. And Jules Verne said, well, folks, don't worry about it. In the future, people will know how to split water to hydrogen and oxygen, and water is going to be the coal of the future. And we've been trying ever since, and it's really hard. There's been one hydrogen era in the 70s that didn't lead very far, and another one in the early 2000s, and also none of them could change thermodynamics. Hydrogen is still a very small molecule, just as it was in Jules Verne time, and because of that, it's very difficult to compress and store and transport. And also an aggressive molecule. And if you put hydrogen at high temperature with stainless steel, and believe me, I saw it happen, and with high enough pressure after enough cycles, you could take this bottle and go like this, and it will crack like it was glass. So hydrogen is not easy to work with. Syngas that you can convert immediately to methanol or something else is a much better solution industrially. So this is what we are trying to do. Where we stand right now. Now, there are closer to practical industrial commercialization solution in thermal energy. People are making salts that are eutectic mixers of salts, eutectic solution that can be used to store thermal energy. But thermal energy solution is localized and it can work for a certain number of hours. These solutions are very close to commercialization. Actually, there are a few companies that already are starting to put it in the plant. They're having problems, but they'll figure them out, and in a year or so it will be part of the plant. In Spain, you can get so much money making solar energy that they don't care how much it's going to cost them for the plant. So they go up to 15 hours of storage. They're building plants like this, not only, but up to that. And I believe that you can have sensible heat storage solution for solar commercialized within the next 2 years. The fuel solution, which is better, will take longer. I don't want to put a number, 5 years or more. Yes?
I'd like to make a brief comment in defense of the higher temperature working fluids for the solar trough technology. I absolutely agree that efficiency is paramount, and that is the major factor driving costs, but higher temperature working fluids and oils could be occasionally useful just because I guess the peak efficiency at 400 degrees centigrade you see for that is with regards to the photons from the solar source. So pushing it up to maybe slightly higher temperatures could give you a better overall economic picture if you could reduce capital costs in other ways by taking slightly higher temperature oils.
You may be right, but the issue here is where are you going to gain? You're going to lose in the optical efficiency, but you may gain some in the engine efficiency because the steam will be at a higher quality steam. And depends how much you gain, how much you lose. You're not going to gain a lot. Okay, you're not going to win by much. Usually those, the problem with the law of thermodynamics, especially the second one, it's really a lousy law. What can you do? What can you do? You're going to get some, but I think if you go do the calculation, if you go from 400 to 450, what I'm trying to search for is where we can go, where really we can make a quantum leap. Okay, so.
My question is about the cost of solar energy.
I couldn't hear.
Once the plant is, installed, bought, and paid for, and the fuel source, sun is free, and you're not paying for, trainloads of coal every month, why is solar energy more expensive than other sources?
Oh, I'll try to explain this in the best way I can, and remember, I don't understand numbers of this kind. Let's take a standard coal plant. What do you have? You have a heat engine, right? 2 large turbines with all the auxiliary around it, and you pay for the capital to put that in the ground. It's not cheap. You got large condensers and steam generators and turbines, but this is what you pay for, right? To put it in the ground. That'll cost you about, what, roughly $1.50 a watt, assuming you don't have to scrub any of the emission, okay? Okay, and now this is your capital investment, and you have to pay for the coal that you put in, okay? Now comes solar plant. He said, okay, I don't need any of the coal. Instead of the coal, I don't have to pay for fuel, but I do have to pay for the collection, okay? So I don't have day-to-day runtime. I pay less because I don't have fuel payments, but my capitals are higher. As it turned out, the collection area more than double your cost. Okay? So here you are, instead of putting $2 billion on the plant, you have to put $4 billion. And you got to finance all that. So it's expensive. The bad news is if we didn't have if we didn't have any carbon emission restrictions, we couldn't compete with coal.
Let's go to the next question.
The solar energy as well as the renewable energies are not available all the time at the same place. So instead of searching of new storage system, is it better economically to connect the electricity grids between different stations in different countries, or to develop a new storage system for solar plants?
I think that connecting the grid is a good idea no matter what.
It is working more economical than storage.
Okay. Transporting electricity is more expensive than transporting liquid fuel and even natural gas. Okay? It's difficult to transport electricity for distances over about 200 miles. And in a place like China, where they have the electricity in the west and people live in the east, they're talking about transportation, grid transportation of 1,000 kilometers. The only way to do it is a very high voltage, so the current is low and the resistance is low. And you can't do it. If you do that, then you can't transport AC voltage because the magnetic field will kill you. You have to try to transport DC voltage. In short, it's not an easy problem. A lot of people are working on it. Okay? I'm not going to say which one is better. I'm just going to point out what can be done. Grid connection and ability to rely on different areas of the grid is a very good thing to do. It's not cheap. How expensive it is depends on how much grid you already have installed. But I can tell you it's not an easy solution. You gotta, and it's probably will vary from one place to another. You essentially have to do both. It's what we've been doing until now. But you gotta do both. Yeah.
You said a few minutes ago that coal that you don't scrub.
I couldn't.
Could you speak louder?
Oh, sure. A few minutes ago you said coal unscrubbed would be around $1,500 a megawatt.
Yes.
And
Even less.
Okay.
Depends. In China, less than 1,000.
okay, but hopefully we're coming to a world that we do want to scrub coal, not just for standard pollutants, but also in terms of carbon sequestration. How far are we off from making solar thermal cost competitive with coal if we truly make coal as clean as it theoretically can be?
Since sequestration is not a mature technology and we don't know what prices are going to be on carbon emission, and assuming carbon is going to be traded, it's a difficult question to answer. But I'll tell you where solar will have to go, sort of like as a road milestones. Coal, without any restriction, you can make electricity at about the cost of 3 to 5 cents per kilowatt hours. Combined cycle, and then if the cost of coal goes up, then that will go up. Combined cycle may be 6 to 8 cents per kilowatt hour with the prices of gas that we have now. The price of gas we had last year, it would have been 10, okay? Solar energy, the best draft system could do if they were at very large scale, under the same condition, let's take 14, and, you know, plus minus cents per kilowatt hour. You need to go to 10. If you did that, 10 is sort of like a magic number here, okay? And maybe 10.5 would do 2, or you'd have to go to 9. But generally speaking, the cost of, call it standard electricity plant, would go up gradually. I can show you a graph from PG&E in California, how they anticipate it to go, because of the, mostly because of the increased cost of the fuels that they anticipate, generally speaking, and carbon emission. But no one can tell you right now what would be the cost of carbon emission, because it's really a political question. We are paying for carbon emission. It's just that we're paying to our health system now, not through our energy system. So 10 cents a kilowatt hour is a good number to remember.
I want to catch you here. You mentioned that it's about 14 cents per kilowatt hour, and solar PV is probably around 25 cents a kilowatt hour. So, and you mentioned that the solar thermal installation, even under contract, is about 1 gigawatt.
Right.
But right now, PV is annual installation is about 6 gigawatt. So, where's the problem? That's my.
I think that the if you look around, you see that a lot of PV installation is done in smaller chunks. And solar thermal, you really can't do that very much. If you want to give the low cost that I was talking about, for instance, you have to build 100 megawatts or more at a time. Otherwise, you know, you have a lot of maintenance costs, and you have, you know, build a small facility is going to take you more money. PV is utilizing or to its advantage regulations. If you put a PV on your house, you can sell electricity to the system, and basically you're not paying all that cost. So it's not because the cost is low, it's because you have regulation that help you do that. In Germany and in Japan, you put there's a lot of PV out there. There isn't any solar energy. There's no solar energy in Germany. And don't let people fool you that they can use the scatters and all that, because if there isn't, there isn't. If there's a lot of scattered solar energy, relatively speaking, it's a very good sign that you don't have a lot of solar energy. Okay? Typically speaking, it would not be worth your time to put solar energy anywhere where the annual installation is less than 2,000 kilowatt hour per meter square per year. Well, in California it's 2,700, in Mojave it's a lot more. In Germany it's about 1,000, okay? So it takes you a lot longer to recover your cost. Still they're putting it up because you could sell solar energy to utility for €1 a watt, or €1 a kilowatt hour. Why not? Okay, so that's, I think the reason is really legislation, not nothing else.
Yeah, so what about water usage, and how does that relate to efficiency?
Water use.
Yeah, the one for the solar plant, you know, water cooling, what are the water consumption needs for the different approaches, and is air cooling?
Okay,
Practical?
if you use Brayton cycles, gas turbines, there's no water use at all. If you use Rankine cycles, or either as a bottoming cycle or as steam turbine, then you have the same problem as you do right now. And as far as I know, there is less and less. You're not allowed to use water condenser anymore unless you're sitting by the sea or somewhere. What people are doing, they use some mist and humidifier and mostly air cooling, air condensers. That lowers the efficiency and increases the cost of the plant somewhat. But I don't see any power plants in the future, or most power plants, built assuming that you use water condensers, and this is how we calculate it. I mean, if somebody would allow us to do that, throw water away, great, but it's not going to happen very often.
Any other questions? If not,
Alex, you've been working on your computer the whole time. You didn't even listen. Do you have any question?
Well, my biggest question is, earlier in the first slide, remember you said the three things, just go trough, conservative, and maybe a little bit crazy, and then the third one is like, do
No, conservative, sensible, and crazy, okay?
So you chose to go crazy, which I think it's fantastic. Where are you in that you said 4 to 5 years? Are you now in year 3 of your craziness, or 2?
Maybe year 2.
Year 2, okay.
Yes. But you see, 4 to 5 years can be 4 and can be 6. And it's not just a matter of how good we develop. Because if we develop, we're going to make mistakes, we're going to learn. And that's the fun part of it, is you know more than anyone else. It's also a matter of funding. Because it could be, my wife tells me, you're always 4 years away. Why? Because I don't have money. And that's the main thing. If you continue to, if you don't do it all the time, you're always 4 years away. Okay? So even if you develop something faster, you want to do the crazy stuff later or something, you've got to move on with it to some extent, or you're never going to get there. Tolkien said, even the longest trip starts with the first step. First, second, third, you got to move.
okay, I think we'll stop here, and there are some refreshments for the reception, and you can ask Jacob more questions.
Thank you.
And for tomorrow, let me give the room number to